In our first video, we talked about research producers and research consumers. So I'm going to expand on that today. At the beginning of each chapter, you're going to see a list of objectives like this. As you're reading through the book, what I would be doing is keeping these things in mind, because this is what your author is saying is the most important things that you should be getting out of that particular chapter. So if you're feeling like there's a whole lot, I'm trying to give you a number of different ways to identify what's most important. So how do scientists work? And psychologists are scientists. Even the ones who become clinicians often are scientists in terms of the ways that they think. First of all, scientists are empiricists. So we like being able to observe, to think about what is actually being done, how is it being done? And we do a lot of testing of our hypotheses. So, many of you have seen Harry Harlow's research on baby rhesus monkeys. One of the questions was, are baby monkeys, baby rhesus, interested in, do they prefer a mother that gives them food or a mother that gives them some contact comfort? And you might stop and think about what you remember from general psych about this. So here's that we're testing two different theories. And what that means then is that we are going to go through a cycle of testing these. We start with a theory, which leads researchers to pose particular research questions, use a specific research design to test our hypothesis, what it is that we think is going to happen. We're going to be thinking a lot about pre-registration. So what happens next, and putting that on the cloud to keep us honest, right? Collect data. And if our data support our theory, it strengthens it. If it doesn't, it's going to ask us to revise our theory or improve our design. Maybe we didn't have enough participants. Maybe we don't have a strong enough dose of our intervention. So, we're thinking about what can we do that would make things work more effectively. Studies that don't prove theories are really important to us. We want to be able to either prove or disprove. And so good theories are falsifiable. And so throughout the semester, we're going to be thinking about, can we replicate our findings? That means, can we repeat what other people have found? What is the weight of the evidence? Is it good? Is it, is this something that we consistently find? Or does this look like a very weak and occasional finding? And can we falsify it? Is there an ability to falsify the theory or the hypothesis? So let me give you an example. This is probably works better for those of you in class. But, I have a rule that makes sequences of 3 numbers, and the order matters. Your goal is to figure out my rule, that theory, data, right? But you can't ask me. You have to determine it. Write a sequence of 3 numbers in the sequence column, such as I've done here. Now, imagine your first guess was 246. That sequence fits my rule, so I'm going to put a check on your paper. And then you should guess what my rule is. So perhaps you guess that we count up by 2s. And, you're not very sure. It makes sense. Okay. Now, one of the things you'll see is that we often want to gather more data, right? So I'm going to talk about a number of different patterns of guessing, some of which are useful and some of which aren't. And I want you to think about what pattern, what style of gathering data is best and why. So here's a person who goes 246. They're correct. They choose a rule, count up by 2s. They're pretty sure. 6, 8, 10. Again, it's consistent with the rule. 12, 14, 16, etc. Now stop for a minute and think, is this a really good way of figuring out whether or what my rule is? Right? And I'm going to argue that it's not. So here's a more scientific pattern of guessing. So we start with 246, and our rule is count up by 2s. But rather than doing, 6, 8, 10, we do 10, 20, 30. And if it's wrong, then we know that this isn't right? Or if it's right. And we do find out that 10, 20, 30 fits the rule, but obviously then the rule can't be count up by 2s. Asking, could I be wrong, leads to insights. So the third time up, they go 100, 500, 894. And they're correct. The student guesses count up, but only count even numbers. And they're pretty sure, but they want to test it some more. And they count up again, or 1, 9, 20. Notice that it's not just even numbers this time. Does that work, right? And so the rule that they're guessing right now is count up. They're pretty sure. Now what they're doing is something that doesn't fit. 27, 13, 4, and they're wrong. By it being wrong, they've learned something important, right? Their mistakes help them. Now, in science, we're almost never 100% sure. Someone's going to come by and wonder about maybe confounds, or going to wonder what happens if we have a larger sample size, etc. And those are some of the questions that we're going to be thinking about over the course of the semester. So, some thoughts. First off, being sure that you're right is different from being right. And you saw that in this last example. Just because you're smart doesn't mean that you don't engage in confirmation bias. And you may remember confirmation bias from your discussions in general psych, where we're looking for information that supports our hypothesis. And that's what the first examples were. Wise people engage in confirmation bias less frequently. You might ask, are there, think about situations in which people would be better off asking, am I right or wrong, rather than just asking, am I right? I'd argue in most cases, right? So some examples, people whose first impressions are always right. People who believe their horoscopes, people who are prejudiced, those who have strong political beliefs and watch a lot of news, but all from the same source. And perhaps you, the last time you were in an argument and you were completely right. So take care, and we'll continue this conversation in the next video.